University of Michigan. Go to it.
Thanks, Leland. Yeah, so I'm going to give a kind of an overview talk about the CYGNSS mission, a little bit of the motivation, and then a little bit about sort of how it works, and then some examples of some science applications that have come out of it. So the motivation for the mission was really driven by this this plot right here. This is it's an annual record that the National Hurricane Center keeps of the quality of their forecasting. And every year they, actually more often than every year, they calculate what the average error is in forecasting the track of a hurricane. The track is where the eye is going to be, or where the eye is. And like, for example, this red line is the one standard deviation error in the estimate of where the eye of the hurricane is going to be 24 hours in the future. So it's their 24-hour forecast. This is the error in their 2-day forecast and their 3-day forecast. And in general, with all of these, there's a negative slope, which means that they've been getting better at forecasting over the last 20 years, and that's a good thing. And over this 20-year period, the error went down by about a factor of 2. Okay, and largely the reason for the improvement in the track forecast is that the primary things that steer a hurricane, that determine where it's going to go, are background environmental fields like the pressure field and the background wind field, and the background temperature field of the ocean. And those things are relatively easy to measure because they don't change that often, and they don't have fine spatial scales, and they're easy to model for the same reason, and they're easy to measure from satellites. And over this time period, the measurements and the models have gotten better at characterizing those background steering fields, basically, for the storm. This is a comparable plot for forecasting the intensity of a hurricane, which is the peak sustained wind. And these lines are essentially horizontal, which means there's been no significant improvement in the ability to forecast how strong a hurricane is going to be in the future. And there's a little bit of improvement here at the end. But by and large, they haven't gotten much better. And the main reasons for that is sort of the opposite of what's going on with the track. Is the main things that determine how strong a hurricane is going to be tomorrow or the day after tomorrow have very little to do with what's going on in the environmental background around the storm. It has to do with what's going on right in the middle of the storm. And that's really because of if you look at the sort of the energy cycle for a hurricane, what makes a hurricane is this positive feedback mechanism that happens where when there's wind blowing at the surface, you get evaporation of water vapor up from the ocean into the air, and the stronger the wind blows, the more evaporation. It's a latent heat flux. So you get water vapor going up into the air that contains a lot of latent heat, and then when that water vapor condenses back into liquid, it releases that as sensible heat, and that's where the wind comes from. So you get more wind when the water changes from water vapor to liquid and precipitates out, and that wind causes more evaporation, and that evaporation causes more wind. That's the positive feedback mechanism that if it runs away, you get a huge storm, okay? So in order to predict what's going to happen with intensification, you need to be able to measure the winds at the surface in the middle of the storm. And there's several things about that are difficult. It's difficult to model because it's a very small spatial scale, so you need really fine grid spacing in your numerical model. It's difficult to measure for several reasons. One of them is that the really high winds happen in the middle of the storm, and it's always raining really hard in the middle of a storm, and it's very difficult for satellites to penetrate through heavy rain to see the wind, so it's difficult observationally. It's also difficult because the winds tend to, in the middle of the storm, tend to change very quickly on timescales of hours, as opposed to these background fields that change on timescales of days. So in order to capture these changes and not alias the sampling, you need to measure often. And that's difficult to do with typical weather satellites because they come back around the same spot every 2 or 3 days. So you can easily alias that signal, that rapid intensification signal when the winds change. So there's a variety of reasons why it's difficult to do, and that's the reason why there hasn't been much improvement. All right? Knots. Yeah, this archaic National Hurricane Center thing. It's not even, it should be miles per hour or meters per second, or at least miles per hour, but it's knots, yeah. So, you divide by 2 and you get meters per second, basically. Yeah. Okay, so the way that, so there's been a lot of work trying to measure the intensity of storms, or the wind speed in the middle of the storms. And one way, that's the most common way to do it, is with optical and infrared imagery from GEO. And the reason it's nice to do it in geo is because then you get samples every 15 minutes, so you can get around this problem of things changing quickly and getting aliased. So this is a picture of a GOES satellite, and this is a typical picture taken by a GOES visible camera looking at a hurricane, and it takes really beautiful pictures every 15 minutes of the cloud top, which is not the wind speed. But there's a whole like cottage industry of techniques developed to try to infer what the wind speed is underneath this cloud cover as a function of little details about the shape of the clouds at the top, called the Dvorak technique. And it's commonly used by the Hurricane Center to estimate winds just from the shape of those clouds. So it's extremely correlative and indirect, and it's not measuring the wind. Okay. Another way to measure the wind is with microwaves, because they can penetrate through clouds at least. And this is a trim imager, and this is an image made by it of the precipitation. So it can measure rain and surface winds as well. So this is a map of the rain measurements made by TRIM, and you can see this really strong set of region of heavy rain that's persistent. It's there all the time. It's called the Intertropical Convergence Zone. It's where about 90% of the rainfall in the world happens, is in that one little strip near the equator. An important takeaway from this image is this number right here. This is a 3-day composite. It's not a snapshot of the rain everywhere at one instant in time the way you'd get with a GOES satellite. It's because it takes 3 days before the satellite starts repeating itself. So you composite all that stuff together, and what the rain here might have been 2 days different from the rain there. Okay, this instrument can also measure wind, and here's the map for the same period of time of the surface winds measured by TRIM, and you can even see some cyclonic organization. There's some storms here, and high winds here, and low winds here, and so on. So it's able to measure winds. So there's two problems with this in terms of using it to seed or force a numerical forecast model for hurricanes. One of them is that it also has a 3-day repeat time, so you'll often miss sudden changes in the wind speed. And the other is, if you notice places where this is black, those are rain flags in the algorithm, because it can't penetrate through heavy rain at, this is like, I think, X-band and KU band, I think. And it can't penetrate through heavy rain. So in general, places where there's really heavy rain in the rain product here are places where the wind speed is blacked out, because it just can't penetrate through to see the surface. So even though it sees winds, it's not going to see winds in the middle of the hurricane, and it's not going to see them often enough anyway if it could. So those limitations with the current techniques for measuring surface ocean winds were really the drivers for this new CYGNSS mission. So what we wanted to do with CYGNSS was measure winds in all precipitating conditions. So basically, we need to move to a lower operating frequency in order to penetrate through the rain. And we need to measure often enough to be able to resolve these really small timescale processes on order of hours. The genesis and rapid intensification phase of the storm, when the wind speed changes really quickly over 6 to 18 hours, there'll be like a sudden change by a factor of 5 in the wind speed, right when the storm starts to intensify. And so these were the two driving requirements or objectives of the mission that drove the design, the engineering design. And the net result of that was 8 satellites. The more satellites you have, the shorter the revisit time. And that's to address this requirement. And then a low inclination orbit, 35 degrees, so that we spend all of our time over the tropics where the storms are. That's A. And B, if you look at how sampling works as a function of latitude when you have a low inclination orbit, the worst sampling in terms of how often you come back to the same spot is right at the equator, and then it gets better and better as you get higher and higher until you get within about 5 degrees of this number, and then within about 5 degrees of that is when you get the most frequent revisits. So we tilted it. If you look at a PDF of the probability of occurrence of a hurricane as a function of latitude, and you match it up with the coverage that you get as a function of incidence angle, we varied the incidence angle until we got a maximum in how likely it is to come back to any given storm often. And so that because there's sort of like there's a tornado alley, there's sort of like a hurricane alley, which is like from about 28 to 34 degrees latitude. It's where most of the hurricanes happen. And well, not so much where they are as where they intensify, because that's the part we wanted to measure. And then again, we use this bistatic GPS technique, which you've heard a couple of talks about, because several reasons. One of them is it operates at L-band, so you get good penetration through rain. And another one is it's passive. The instrument that we fly is passive. We don't have to fly a transmitter, and that makes the satellites be very low power and low cost, and that was why we could afford 8 of them for this relatively low cost cap mission. And we wanted that number to be as big as possible to get a revisit time down. Okay, so this is the basic technique of bistatic GPS radars. GPS is transmitting. There's a spot here where angle of incidence equals angle of reflection, the specular point, where most of the scattered signal goes in that direction. A little tiny bit of it goes back in the backscatter direction for a conventional radar. And then our Cygnus satellites are sitting here making those measurements, and we're after wind speed, right? And the idea of how you can measure wind speed from a specular scattered signal, you can see sort of qualitatively from the behavior of specular or quasi-specular scattering at optical wavelengths. So here's optical bistatic scattering where the source is here. Actually, the source is the sun, but it scatters off the moon, comes down here, hits the lake, and then your eyeball is the receiver here. And the water is really smooth in this lake, so that moon is pretty smooth. It almost looks like that moon. It's actually a little bit of roughness around the edges, and you could actually calculate the roughness statistics of the ocean by looking at just how imperfect that circle is, right, at optical wavelengths. So when the wind blows, this happens, right? You get diffuse scattering. The specular point might have been right about here, but you get all this other scattering away from it in the glistening zone, in the quasi-specular diffuse scattering zone. If you can image how much scattering you get at different places away from the specular point, you can calculate how rough the surface is, and from that you can get the wind speed. That's the way the measurement works. And this is an example of that. This is one of the first measurements made of GPS bistatic scattering from the ocean, made from space. And this was in a tech demo mission by Surrey Satellite Technology, who also built our receivers for Cygnus, but this was when they were first developing the technology to do this. It was using a modified GPS navigation satellite and or GPS navigation receiver on a tech demo satellite. And here's the specular point right here of the reflection. This is L-band scattering off the ocean surface, and this is diffuse scattering away from it. And the exact shape of this thing and how bright it is here compared to here has the same sort of information as how bright this is here compared to this, and you can back out the wind speed from that. And this is an example of that. These are 3 different measurements made by that same satellite as it flew over an instrumented buoy that was measuring wind speed, and these are the buoy measurements here. This is like a typical wind speed. This is kind of windy, and this is pretty calm. And you can see that the windier it is, the rougher the surface is, and the scattering moves away from the specular point and spreads out to other places. So these images, delay Doppler maps, these are the things that we measure. Every second we make a snapshot of the scattering as a function of, this is the Doppler shift of the signal, and this is the range gate of the radar, basically. So it's range versus Doppler, and those things can be mapped into position on the ground. So it's basically a 2-dimensional map of the scattering cross-section around the specular point in the glistening zone, the quasi-specular scattering. And so that's the data that we get our wind speed from. And this is the forward model for our measurements. There's the GPS transmitter here, transmitting power, transmitting gain. This is the scattering equation. This is what we want. This is our level 1 data. That's the scattering cross-section of the ocean right there. And this is our data as a function of time delay, the range gate, and the Doppler shift. And all you got to do is you make this measurement, you invert that equation in your level 1 calibration to solve for scattering cross-section, and from that you get the wind speed. And the way we get the wind speed from that, we use 2 different algorithms to get the wind speed. One of them is borrowed from conventional ocean scatterometry, which is a backscatter radar, and the other is borrowed from conventional radar altimetry, which is, it's like a radar altimeter, you know, it looks straight down and times the signal and how long it takes to come back to measure sea level. And it's actually both a backscatter and specular forward bistatic scattering radar. It's the same at that one particular angle. And yeah, for a conventional scatterometer, you just measure how strong the signal is, and that's related to wind speed. And for backscatter radar, the windier it is, the rougher it is, the more backscatter you get. With a forward scattering measurement, it's the other way around. The rougher the surface is, the less of it scatters in the forward direction, the more scatters other places. So what we do is just take the average of that little box right there. That box corresponds to a 25-kilometer area on the ocean surface, and we just average that, and that's inversely proportional to wind speed. So that's comparable to a conventional scatterometer measurement, just sigma naught mapping to wind speed. And then the other way to do it is when our signal, when we get our scattered signal, it shows up as a function of time because we have range gates. And you look at the time dependence of the signal, and that's what this is. This is taking this signal here and integrating out the Doppler dependence, just integrate across this way so you get a one-dimensional function of time only as a function of range. And that's what this is. This is it's called the delay integrated waveform. So, so this is range gate, and what happens is the windier it gets, this is going from low wind to high wind, the windier it gets, the more tilted that return pulse is, because if the ocean is perfectly flat, you get this nice sharp return. If the ocean is rough, it spreads out over time. So we measure the slope of the leading edge of this return pulse. This is very similar to the way altimeters measure wind speed, by the leading edge slope. So we do both. We measure leading edge slope, we measure the delayed Doppler map average, which is the sigma naught. Both of those map onto wind speed, and then we use this minimum variance optimal estimator thing to combine the two together in an optimal way, because each one of them has partially correlated errors, and you can do a weighted average of the two to get the best wind speed. So that's the wind speed that we use. And this is the model function that maps sigma naught to wind speed. This is wind speed here. This is the scattering cross section. Log base 10 of the scattering. So this is like a scattering cross section of 10. This is a scattering cross section of 100. And there's two different model functions here. One is called the fully developed C's model function, and the other is the limited fetch model function. And the reason for that is there's not a one-to-one mapping from scattering cross-section to wind speed. And the reason is the thing that we're actually measuring is not wind speed, right? It's the scattering cross-section is really related to the roughness of the surface. And what roughness that is, it's a roughness over a certain range of the spectrum. If you looked at a roughness spectrum or a height probability distribution of the surface, we're only sensitive to a certain range of wavelengths of roughness. And the range that we're sensitive to is quite a bit different than the range that a backscatter radar is sensitive to. With a backscatter radar, most of the sensitivity is determined by the Bragg resonant condition, where you have, you can take the surface and take the Fourier transform of it and break it up into all these different little wavelengths, different components at different wavelengths, and there'll be a component at the fundamental Bragg resonant frequency for your transmitting signal for a backscatter signal. And it turns out that 90+% of the scattering cross-section is determined by the part of the roughness just at that Bragg wavelength, okay? And for typical scatterometers, the Bragg wavelength is a few centimeters. So you're sensitive to these little capillary waves on the ocean surface, which are directly forced by the wind speed. But with forward scattering, there's no Bragg resonance at all. And that has a fundamental effect on which parts of the roughness spectrum you're actually sensitive to. We're also sensitive to the small capillary, we're sensitive to the capillary waves, just like backscatter, but we're also sensitive to much longer waves, the swell waves, okay? And the way ocean surfaces develop roughness in the first place typically is there'll be wind blowing, and that will roughen the really small scale capillary waves, and then there's an energy cascade where it cascades down to lower and lower wavelength or frequencies, longer wavelengths. And because waves propagate dispersively in the ocean, long waves propagate further before they dissipate than short waves. Short waves dissipate really quickly and locally. So if you only are sensitive to the small capillary waves, you're going to be very sensitive to the local wind only, because And the long waves will have a correlated component to the local waves, but they'll also have a component correlated with things like some giant storm 500 kilometers away yesterday, because those long waves can propagate a really long distance. So what happens is we're sensitive to the actual, this long range of this roughness spectrum, not the winds. And if the seas are fully developed, which means the winds have been blowing in the same direction for about the same speed for at least a few hours in practice, that's what that means, then the correlation between the small scale waves and the long scale waves is very, very high, and we're essentially just measuring the wind. And that's what this model function is. And this model function accurately retrieves winds 99% of the time in the ocean. One place where it breaks down is if the winds are changing significantly in direction or speed within a few hours, and that happens right in the middle of a hurricane, because the winds are changing primarily in direction, because they're curving around cyclonically. And because of that, the the local long wave swell doesn't have a chance to build up from the small waves as much, so there's less long wave swell per unit short wave capillary waves, and that tends to lower the scattering cross-section, raise the scattering, it would lower the scattering cross-section for a backscatter radar, it raises it for a forward scattering radar, and that's the reason why this whole thing tilts up like this when you're in a hurricane, because of this. So this is a fundamental difference between backscatter radars and forward scatter radars, and it makes the situation complicated. If you're right in the middle of a hurricane, this is a reasonable model function. If you're far from it, this is a reasonable model function. What to do in the transition zone as you get within a few hundred kilometers of a hurricane is not at all clear, and that's like an active research area for Cygnus right now. Okay, so this is some pictures of the hardware. This is, that's not playing very well. This is the deployment that happened about 15 minutes after launch. All 8 satellites were on one rocket and went up, and they got released by these little spring-loaded things that pushed them out in slightly different orbits. They went off in slightly different directions so that the orbit velocities were a few hundredths of a percent or thousandths of a percent different from each other, and that caused them to settle out at slightly different altitudes, which had slightly different orbit velocities, which let them spread apart from each other. That was the reason we did that. And this is all 8 of them getting tested a few days before we mounted it on top of the rocket. This is a big vibration table, and this is the way it was like set up just before launch. And then you can see after they get launched, the solar panels open up and they start doing their thing. See, one other thing you can see from this is down in the bottom of these, you can see these 2 big antennas looking down. Those are the science antennas, the L-band antennas. And then there's a little tiny navigation antenna on the top, just a little half-wave dipole thing, that a half-wave patch antenna to get the direct signal. Okay, so here they are all opened up, orbiting along. And this is an example of the coverage that we get. This is one orbit for all 8 satellites. It takes 95 minutes, and that fills in like that. And then this is after 24 hours, so it does a nice job of filling in most of the Earth from, this is plus or minus 35 degrees. We get a little bit higher than that and a little bit lower because we can see out pretty close to the horizon, which is another 3 degrees or so of latitude. And yeah, if you look really closely right in here, we've never actually gotten a specular point all the way up to Ann Arbor, just like 42 point something degrees. But we've gotten some stuff in southern Ohio. That's as far north as we've ever gotten, but it's not quite here. This is a video of how the sampling works, just to give you an idea. So all 8 satellites are more or less evenly spaced out around the orbit plane, like this. And then these are the 2 antennas, science antennas. There's one on the port side and one on the starboard side looking down at the ocean. And then these are all the specular points that could, in principle, be processed. For every GPS satellite transmitting and Cygnus satellite here, there'll be one specular point on the ground, right where angle of incidence equals angle of reflection. And as soon as that specular point enters into our antenna pattern, we know that, and we acquire it and start processing the scattered signal. And then these lines here are just like the time history of the scattered signal. So we measure winds along these lines from each one of the satellites. And each one of the satellites has 4 GPS science receivers looking at 4 different scattered signals from the bottom. And then there's 8 satellites. So if you add all those together, 4 per satellite, 8 satellites, you get 32 samples that we're taking every second. And this is an example of, I think this was like April 25th was the first day after launch when all 8 satellites were running in science mode after we'd finished our engineering commissioning. And this is just a map of the winds that were retrieved over the course of a day as the satellites are orbiting along. This is an example of how good a job we're doing of measuring winds. This is a Mera-2 reanalysis. This is like one of the sort of industry standard models for what the wind speed is everywhere that's derived retrospectively from assimilating a whole bunch of different satellite data together and different models together and surface buoys and things. So that's the ground truth wind basically, and this is our retrieved wind. So they match up pretty well. And this is the average difference between them over a year, just to show that it's relatively unbiased. And so anyway, that's our wind speed product. This is the fully developed Seas wind speed product away from storms. In storms, it's a lot harder to directly validate point by point what the wind speed error is because things are sort of chaotic. And a better way to assess the quality of the of the wind speeds measured in the middle of a hurricane is to look at whether they're actually helpful when you try to use them in a hurricane forecast model. So that's what we're doing, and I'll show you a couple of examples of that. So this is just some sort of eye candy pictures of hurricane overpasses. This is Hurricane Dorian. From earlier this year. So these are like 1 hour overpasses by the constellation of the storm for, while it was heading towards the US. And then these are taking 3 hours of data over this, when it was doing this overpass. These are just the raw data, gridded data products that are just like this point here and this point here could be, 30 minutes apart or 40 minutes apart. So things are sort of blurred out in the middle. This is a 3 hour composite where for every sample, we regrid the data with a relative storm-centric coordinate system where you keep track of where the storm center is over time, over the 3 hours, and you just shift the coordinate system for every individual point. And when you do that, you clean it up a lot, and you can see the structure of the storm a lot better in storm-centric coordinates. So anyway, this is the data that gets input into a forecast model, and here's a couple of examples of the forecast scale impact. So this is HWRF is like the official operational weather forecast model used by the National Hurricane Center for predicting where the storm's going to go. And it's it's this physical model that you initialize it with a bunch of observations, and then you let it run, and then the storm evolves internally, all right? And there's many intermediate data products that it makes along the way to calculating where the storm's going to go and how strong it's going to be. And this is just one example of it. This is the standard model they run. This is the model using Cygnus data. And what this is a forecast 24 hours into the future of what the winds in the storm are at 3 kilometers altitude. So it's developing storm evolution with a whole bunch of different slices at different altitudes for temperature and pressure and wind and a whole bunch of stuff. And so this is just one particular one, is what the wind is at 3 kilometers. And you can see with the standard model, there's a lot of azimuthal symmetry here. And when you add, this is with the Cygnus data added, the whole storm tilts over like this, and it's stronger up here in the northeast quadrant. And the reasoning here is that we've got this extra information about the latent heat flux coming up off the surface because we're measuring the winds in the middle of the storm, and presumably that gives you some information about what's going to happen to the winds later when that heat is released as sensible heat, right, a day later. And we picked this particular case to compare to because a day after this forecast was run, the Hurricane Center flew a Hurricane Hunter plane through the storm and made in situ measurements of the storm wind at 3 kilometers. And these are the measurements that they made, and you can see that it's got that asymmetry there that we picked up that this one didn't. So that's a nice sign that sort of the inner workings of the forecast model are predicting physical things that are real. And then sort of the punchline is whether you can predict intensification better. And here's an example of that. This is a hurricane model, Michael, which was actually very poorly forecast by the HWRF operational models. And this is, let's see, this black line, this is the minimum pressure in the middle of the storm, which is a good way to measure how strong a storm is. And this is what really happened after the fact. This is a best track estimate of the minimum pressure. You can see the steep drop in pressure right here. That's the rapid intensification phase when the storm got really strong in a short period of time. This red line is a forecast of that, and back here at time 0. So the forecast by the Hurricane Center missed this rapid intensification about 2 days, 2 days later. It didn't really deepen there like it should have, just because they missed the forecast. So we took HWRF and ran it at the same point again, inputting the Cygnus data also, so that we had the latent fluxes and the heat fluxes at the surface. And this is what you get when you add it in. And it picks up that rapid intensification a lot better because you've got a better handle on the energy getting pumped into the storm. So that's good. All right, I've got a few slides left here about measurements over land. So Cygnus was designed as an ocean hurricane weather forecasting mission, but it turns out that the measurements, we leave it on all the time, and we've been getting measurements over land from day one, and we've started looking at the land data, and there's a lot of utility in it. And this is an example of that. These are some results by other people on the science team that I'm just kind of picking and choosing some of their results. This is a map of the Cygnus SNR over a month, and the SMAP soil moisture over a month. And you can see there's a clear, just sort of qualitative correlation between the two. So we're sensitive to soil moisture because we're sensitive to the dielectric properties of the surface from the forward scattering. This is one particular SMAP CalVal site measurements of the soil moisture over the course of a year. And the gray is the in situ probe of soil moisture. And I forget which of these. One of these is Cygnus, and one of these is SMAP, the red and the blue. Anyway, they track really well. So we're able to measure soil moisture with about 4% by volume RMS error, which is comparable to the SMAP retrieval. So that's a good sign. And then just in the last couple slides here, this is actually another way of presenting the same information that Leung showed earlier of the difference between coherent and incoherent scattering. With incoherent scattering, the signal comes down, scatters all over the place in different directions. The sensitivity of our receive power to range goes as 1 over this range squared times this range squared. Whereas when you have coherent scattering from a smooth surface, so you can sort of use image theory and think of the transmitter as sort of virtually being down there. And the sensitivity goes as 1 over R1 plus R2 squared. And if you look at the difference between these two, the ratio is about 30, well, you said 35 dB. Yeah, it's between 31 and 34 dB for most of our data, if you actually calculate the real difference. So what that means is the coherent signal is 1,000 to 5,000 times stronger than the incoherent. And what that does is, even if you have a really tiny little smooth surface, typically standing water, inland water, a little surface that's way, way smaller than this huge incoherent scattering area, it'll dominate the signal that you receive, even if it's really tiny. And I'll give you an example of that here. This is a map of one part of the Amazon River measured by the SMAP passive microwave instrument with about 30-kilometer resolution. This is the same exact part of the river measured by the radar on SMAP when it was working, and it has about 3-kilometer resolution. And you can see it picks up a lot of the little details a little better than the 30-kilometer resolution. And then we made an image of the exact same spot with CYGNSS with this huge coherent scattering sensitivity, and this is what you get. So it's way, way better than 3 kilometers. It's these little things that are resolved are way smaller than the Fresnel zone of the reflection, and it's because even something 100th as big as the Fresnel zone is going to be 10 times bigger than everything else because you've got this 30 to 35 dB advantage in the SNR of the coherent. All right, and this is one last example of this is making measurements of as we flew over this little tiny river. Well, it's about 100 meters wide, the Pascagoula River in Mississippi. It's the largest river in the U.S. that has no flood control, and it's because of a bunch of environmental concerns down here with some wetlands, and I don't know, maybe there's some little snail going extinct or something. And for whatever reason, they don't dam this so that it floods routinely when it rains hard. And so we made a bunch of overpasses of this with CYGNSS to try to measure the change in the width of that river. And this is the flow rate of the river measured by a it's very well instrumented. So there was a huge rain event, and then the flow rate went way, way up because there was a lot of water from the rain. And these are times when we flew over it with CYGNSS to try to measure the width. And these are the width measurements. So this is the signal strength over time is the blue. And then this part right here is when we went right over the river, all right? And all we did was just take the little part when we go over the river and just fit a power series to it, a quadratic to it right here, and then look at how wide the quadratic is for each one of these cases, and then related it to the flow rate. And this is what you get when you do that. You get this really high correlation between the width of the river as derived with this thing called the associated GNSSR width. It's just how wide the part of the waveform is when it goes over the river. It's super highly correlated with the flow rate because this is an undammed river and the water just overflows its banks when you get a lot of flow. So this is another application for CYGNSS to measure river flow rate remotely, and it's possible even with this little 100-meter wide river because we have such high signal response to these smooth surfaces, basically. And I think that's it. I'll stop here. Thank you.
All right, time for one question.
Yes, very interesting presentation. Thank you. My question is...
I'll be here at the reception afterwards. Just.
My question is I guess in correlation to the backscatter type of like rapid scatter, quick scatter. With those devices, you have to take multiple azimuthal measurements in order to unambiguously invert their GMF that's associated with their measurements. In your setup here, you take one bistatic measurement. Am I correct?
Yeah. So there's good and bad news about that. I mean, it makes it easier for us that we only need one measurement. That's the good news. The bad news is the reason they want more than one measurement is because the scattering cross-section in the backward direction is sensitive to both wind speed and wind direction. And you get different azimuthal looks at it, and you can resolve what the direction is in addition to the wind speed. So it's bad for them because they need two measurements. It's good for them because they can measure direction as well. We're not hardly sensitive at all to direction, so we can't measure direction, but we don't need more than one look. Right? Yeah.
Thanks.
Okay? All right, thanks.